Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon everyone, here and in the virtual world. It's my pleasure to introduce Mark Pauly, who's a professor at ETH Zurich. Mark did his PhD at ETH and then a postdoc at Stanford. He's done a lot of work on point-based and 3D modeling representations, both rendering and also simulation as well more recently. And he'll be talking today about symmetrization.
Thank you, Yus. Welcome, and I'm happy to have this chance to present some of my work here. So I will be talking about symmetry, finding symmetries, and making objects more symmetric. But before I go there, I thought I would start out with a little overview of my research to give you a more general idea of what I'm doing. And generally, my research centers around shape, 2D shape, 3D shape, also sometimes higher dimensional geometric shapes. And there's sort of three cornerstones to my work. One is in object analysis. How can you derive interesting properties from 2D or 3D shapes or family of shapes? Then geometric modeling. How can you create and manipulate geometry? And then also animation. How can you bring them to life? As Yus mentioned, some of my past work was concentrating on point-based graphics. This is actually something I'm not really actively involved anymore. This is an overview of the work I did during my PhD. I put these images in gray because this seems like a long time ago to me now. So on to more recent things. What I want to do now is give you a little fast-forward overview of the different aspects of my work. So this will be like 10 minutes of a few video clips just to give you this brief overview. If there's anything you find interesting, we can talk about it later. And then in the second part of my talk, I will come to more concrete projects. So in shape analysis, one of the things I've been working on is surface reconstruction. We did a bunch of papers on this. One of these papers, and you see a clip on the left here, was using examples to reconstruct 3D geometry from point samples. So if you have a laser scan like this one, and you want to reconstruct its geometry, the idea of our approach is to use example shapes that we retrieve from a database, so similar shapes that you found before, warp them to match the input data, and then combine different models, different parts of models using automatic segmentation to retrieve a final reconstructed surface. So the theme here is reuse, work that you've already done before, you don't want to repeat again. On the right, you see a little clip of a project that we've just started. So this is an input data set we get from a fast structured light scanner, and we're trying to reconstruct now these dynamic shapes. So here I don't have anything in terms of results to show. This is something we just started working on. Another area that I've been working on is physics-based animation. Here's a little video clip of something we did a couple of years ago on modeling fracture. And the goal here was to be able to represent very diverse types of materials. So you saw this very plastic bubblegum-like structure, and here you have a very brittle stone-like material. And we used a particle system and a meshless surface to achieve that. Then other work in animation is about control. So this is a fluid simulation, and the idea was to simulate a fluid as realistically as possible, but give the animator control to make the fluid behave in a way that it naturally would not do. So this system allows us, for example, to have the fluid get into certain shapes. Here you see this like Terminator kind of inspired sequence where the fluid flows up the stairs and forms this character. And this year at SIGGRAPH, just recently, we presented some work on fluids that uses adaptive sampling. So here the idea is to be able to focus computational resources in the regions where they're needed. So we have this adaptive particle sampling, which you can see here in this cross-section view. So dynamically, particles are up and down sampled. It's a little bit better visible here in this 2D animation. And the focus in this work was really on using geometric information to do this. Of course, the goal was to get fluid simulations that use significantly fewer particles but are at least qualitatively indistinguishable from the high-resolution model. and going on in this very rapid fast forward of some of my projects. This is another paper we presented just a few weeks ago at SIGGRAPH. This is about geometric modeling. We call it embedded deformation, and what it does is it computes a space deformation using this auxiliary structure that we call a deformation graph to embed an object that's embedded in space. So it allows you to embed basically any kind of geometric representation interactively. So we can also handle, for example, animated sequences. So here you see an edit of this horse animation using keyframing. So you do an edit on one of the keyframes, and then the system propagates these changes throughout the entire animation sequence. And it's a nonlinear optimization that nicely preserves the details of the original animation, as you will see in the results in a second. Actually, there are more edits than just this one shown here. What you see here is first the legs get lengthened, then the head turns, and then this neck gets enlonged. So you don't have to have access to the original animation data, you just need the geometric sequence. And of course you can extend this to other representations that can be embedded in space. Here you have a particle simulation that you can directly interact with, and this allows you to change simulations which would be very hard to manipulate by changing physical parameters only. So you can do a lot of non-physical things in that way. A very similar idea, but technically quite different, is a paper that will be presented in a few weeks at Eurographics. It's also a space deformation. It follows the same kind of design principles, but uses completely different underlying technology. So this is an extension of a paper that we presented last year at SGP. It uses an underlying spatial structure, here an octree type grid. And these individual cells that you see are glued together by some nonlinear energy. And whatever is embedded in the space gets deformed using an RBF interpolation. You see the 3D equivalent. It's also a nonlinear optimization that has some very nice properties in terms of detail preservation. But with this space deformation, it allows you to really decouple the complexity of the deformation from the complexity of the object. And one thing that's really nice about this is it's extremely robust. So what we did in this last example, we squished all of these cubes into one single point, applied random rotation to the cubes, and let the optimization try to find the global minimum, and it was able to recover the original state of the object. Okay, so this was a rapid pace fast forward to some of the projects I've been doing. Now we can slow down a little bit and come to the main topic of today, which is symmetry. So symmetry is something that we see a lot in our world. It's fundamental in the laws of physics, for example. It appears in a lot of biological structures, a lot of man-made structures as well. And it very often corresponds to function. So there's a lot of interest in finding symmetries, for example, to reduce complexity, as this quote motivates, to do compression, to also recognize or retrieve objects. If that's not motivation enough, I have another quote by a biologist, which might, increase the motivation of why looking into symmetries is important. So the goals of this project are twofold, and this is actually a picture that you sent me. I want to find symmetries in 3D geometry and output something that looks like this, that gives you the symmetric structure of the object. It actually turned out that this 3D model that we have here, that we found on the web, is quite different from the original real castle. It has significantly more symmetries than the original model, but that was good for our algorithm. And in the second part, I will talk about a project that we call symmetrization, where the goal is to enhance existing symmetries in models and make them more symmetric. Before I go into the details of these algorithms, let me first make more formal what I mean by symmetry. Symmetry under what? We're looking basically here at invariance under a certain class of transformations, and we consider reflection, translation, and rotation. And in the first part, we also consider scaling and all combinations of these. And here you see some examples of where these types of symmetries appear. And one thing you can notice here is some of these symmetries are global, for example, in the butterfly. but some are only partial. They only affect parts of the model, and some are exact and some are only approximate. So the butterfly, for example, is not perfectly symmetric. There's some variations in the growth, and we want to be able to handle both partial symmetries and approximate symmetries. There's been a lot of work on this. In the early days, people focused mostly on global exact symmetries. A lot of people worked on this in computational geometry, and only recently have people looked into more general classes of symmetries and their applications in geometric modeling, computer graphics. I will not talk about these papers, but you can look them up if you're interested in this field. So what I want to do now is do sort of a step-by-step walkthrough through our algorithms and some of the insights that we gained in this project. And I will do this with a very simple example. So here you have this very simple 2D butterfly, and we're looking for symmetries in this example, and we're only looking at reflections here. So what is a reflection? If you pick an arbitrary line here, we can ask ourselves, is this object symmetric with respect to that line? What does that mean? Well, if I apply the reflection, this is what you get. I can go back and forth, and you can ask yourself, is this a good symmetry plane? Now, the first thing to try to formalize this a little bit is that we want to parameterize this specific transformation that we're looking at. So this line here in 2D can be parameterized by a distance to the origin and an angle to some fixed axis. And with these two parameters, we can map that specific transformation into what we call a transformation space. Basically just a space where every point denotes a specific transformation. And this notion will be very important throughout the talk, that we can represent the symmetries that we're looking for as points in this transformation space. So what does it mean now for this object to be symmetric with respect to that plane? If we again apply the symmetry and overlay the two objects, you get a symmetric object. And you can see in the dark gray region, these are the parts that actually overlap from the original to the reflected model. And now you could define a continuous quantity that measures the symmetry. And to compute this, you could, for example, rasterize this image and just count the number of pixels that got covered by both models. And this gives you a symmetry score, which in this case would be something like 1/3. So you get a score that is 0, the object is completely asymmetric, and 1 if it's completely symmetric. So how could we go about finding symmetries? Well, we could just sample our transformation space. So if we pick another point, we put the line there, we apply the transformation, and we compute a symmetry score. This one's a little bit better. And then we do this for multiple of these points. And you can see, of course, that this kind of random search in transformation space will take a long time before, by chance, you might hit the perfect symmetry. Right? So there's basically two insights here that we can exploit. The first insight is that the search space is actually too complicated for us to do something naive. In this simple example with the butterfly, we only have 2 parameters for our transformation. But if we're looking at rigid transforms plus scaling, we're dealing with a 7-dimensional space, and you can't just naively walk through that space to find your symmetries. And also this global computation, rasterizing the object and counting this overlap region, is too costly. So the idea that we have is that we first need to confine the search space, and we do this using pair relations. And we also reduce these global computations to purely local ones. So let me explain how that works. Again, we have our butterfly, and now we pick 2 points on the boundary. Let's say at this point at random. These 2 points will define a reflective line uniquely. It's the orthogonal bisector between the 2 points. And now we can look at the geometry only in the local neighborhood around these points. So we can ignore the rest of the model, and we just look at how the geometry locally gets mapped under this transformation. And you can see here that this is not a very good match. So in our transformation space, this specific pair maps to 1 point, and we give it a low score because it doesn't really give you a good match locally. And now you can pick another pair at random, this one, ignore the rest of the geometry, apply the transformation, see that this is a good match, and this will give you a stronger support for the specific symmetry. So these points are now local evidence for a specific symmetry plane, but of course, since they only consider very little pieces of the whole object, they are not in themselves very strong in their argument. But if you do this for a lot of point pairs, you can accumulate local evidence of symmetry and then look at this distribution, and it becomes a little bit more clear if you look at a density plot, as you see here on the right. Wherever you get a lot of point pairs agreeing on the same transformation, you have strong reason to believe that there actually is a symmetry there. And in this case, you see this one strong peak, and this corresponds to this reflective plane that we were looking for. So the idea here is now that by applying all these local operations on point pairs, we can confine the search space to those regions where we have a lot of local evidence. And then we can use clustering techniques. We use mean shift for this to extract the symmetries. And once we've confined this search space, we do a verification stage where we actually check if this cluster was not some accident, but does really correspond to a true symmetry. And this is really the core idea of the algorithm. If you do an analysis, you can actually prove that under some assumptions on the sampling and the geometry of your shape, that you will find the relevant symmetries with some probabilistic guarantees. So let's look how this works in practice. Here we have the castle again, and you can see that if you remember the picture, this model now is much more symmetric than the original castle actually, but that's most likely because the designer built it by exploiting symmetries. He didn't model each of these towers separately. He modeled them once and then copied them. So there's a lot of symmetries in this model. I'll show you a little video clip that shows our algorithm in action. You will see two colors, a golden and a black part that illustrates the detected symmetry. And then we take out 1/2 of that and keep operating recursively on the rest of the geometry. So the first symmetry that gets detected is this global one. And then this algorithm proceeds in finding symmetric parts within this model. We always take the biggest one that we find currently and remove it from the geometry. And this is done to up to some sampling threshold, and then here you see the bounding boxes of these parts that have been taken out. So such a structure, for example, you could use directly for ray tracing or other tasks. If you shoot a ray and you hit the big box, you just apply the transformation recursively until eventually you hit a real piece of geometry. So what's happening here is really data reduction. In the end, you're left with 14% of the original without any loss in information. That's because this object has such perfect symmetries. And this can not only be used for, say, compression, but it can also be used to reason about the construction of this object. What rules have been applied in its design, for example. Because symmetries play a lot of, are typically very important in design of buildings and architectural structures. Here's a slightly more difficult model. This is a hand-sculpted model that has been scanned. And what the algorithm finds is symmetries of the head, the feet, and the main body. But these symmetries are now not perfect. You can see here in this color-coded graph the deviations from perfect symmetry. Because this is a hand-sculpted model, it is not perfectly symmetric. And you see that there's quite a bit of deviation. But still, this result was a bit unsatisfactory to us, because if you look at this creature, what we fail to recognize is this global symmetry that we as humans detect, this reflective symmetry along the axis of the spine. That's because the spine is bent. Here's an illustration of that in 2D. So you have this outline of the lizard. What our algorithm finds are two strong clusters in the regions of the feet. That's because there we get a lot of point pairs that correspond to the same symmetry plane. So this is, again, just looking at reflections. And what you see here is, so this is the plot in transformation space. And you get this one-dimensional structure in here. And this corresponds to the symmetry plane of the spine slowly and smoothly varying across the spine of the model. And we get these two clusters simply because we have more geometry here that creates more density in this plot. But we're not able to recognize the fact that there is this global symmetry under that deformation. And this leads us to the second part. Here it's stated sort of the opposite way. When we started this project, our goal was to extend the type of symmetries that we can detect. And we want to be able to find these kind of symmetries under deformation. But the approach we came up with was sort of like analysis by synthesis. We're trying to make objects more symmetric, and as a result of that, we can actually detect more complex symmetries. And the central idea here is that we compute a deformation of the original object, and that deformation is driven by an optimization in transformation space. So the goal is to make an object more symmetric, and if you look at the symmetries in transformation space, it turns out that these operations actually map to some simple geometric operations. So we'll try to walk you through this in a very simple example here. This is sort of the most trivial thing you can think of. Again, we're just looking at reflections. You have 2 points given, and you have given a transformation. And now you want to make these 2 points symmetric with respect to that plane. So basically what that means is you want to move those points so that they become symmetric, but you want to move them as little as possible. And it's a very simple construction that allows you to do that. You apply the transformation or its inverse to both of the points. This gives you these p primes. And then you take the average of the original and the corresponding reflected point. And these 2 points by construction are now symmetric with respect to the plane. And you can also show that they minimize the displacements from the original positions. So that's sort of a very simple solution for this problem. Of course, what we're looking for is a little bit more complicated. So let's go one step further. In this example, we have not given a transformation. What we have given is a set of corresponding point pairs. And this is indicated by color here. So the 2 yellow points, for example, correspond to each other. They again map to a transformation in transformation space. So we have a point here. You can do this for all the other ones. And now what we're looking at is, at the same time, the best possible transformation and the corresponding set of displacements that makes these corresponding point pairs symmetric with respect to this transformation. And what turns out is that you can find a closed form solution for this. And in this case, it's actually very similar to a least squares plane fit. And what you can also see in this illustration is that the optimal position is not simply the centroid of the transformations of the individual points. If you go to rigid transformations, then finding this optimal transformation is similar to ICP. So you can do an SVD of a specific matrix. It's slightly different from what you do in ICP, but conceptually it's quite different, quite similar. So this is nice. If we've given correspondence, we can find this optimal transformation. Now, of course, we don't have this correspondence in general, but for this, we use the first part, the symmetry detection, and then iterate this process. Yeah?
So how would that come into play for this, in this scenario?
So if you didn't have, here I'm just looking at reflection. And if you're trying to find this plane here, it basically amounts to something that's similar to a least squares plane fit. If you're looking for a rigid transform, rotation and translation as your symmetry, then it becomes similar to an ICP type fitting. But the important thing is you still have a closed form solution, because you're looking at the same time for this transformation that gives you the minimal displacement. But it's a little bit easier to see in this 2D example. So now what we had in the beginning for the symmetry detection was this. We were sampling the objects randomly with points. We grouped 2 points. 2 points define a transformation. And now we want to do something that is similar to this to deform the object such that it becomes more symmetric. Now, if you look at this random sampling, there's actually 2 reasons why things are not perfectly symmetric. If we just sample an object, even if the shape is perfectly symmetric, these samples don't have to be symmetric because they're independently sampled. So the first thing that we need to do is optimize the positions of the samples without changing the geometry. And the second reason why things could be non-symmetric is that actually the shape is non-symmetric. And in the second part, we optimize the geometry by actually computing a deformation. So the first part looks something like this. Here you have a perfectly symmetric shape. Again, the correspondence is coded with colors. You get this plot in transformation space. Now from the formula I've shown you before, well, I haven't shown you the formula, but from the result I've given you before, we can compute the displacements that make these points symmetric with respect to a plane. These are these white points here, but now of course they move off the surface. And because we at this stage only want to optimize the positions, we just project them back. This gives us these squares and iterate this process. So the squares now again have transformations, and you see how they already moved closer. So you can see the spread of these points gives you a measure of how unsymmetric things are. And here you can see that they've already moved closer. And then you iterate this process, and after a few steps, the samples are distributed perfectly symmetrically. The other part is that what happens if your object is actually not symmetric. So now, after we symmetrize the samples as much as we could, we need to deform the shape. And I will show this here with a very simplified example. If we have two point pairs that map to two transformations, we want to symmetrize them. That means we want to move them to a single point in transformation space. So for example, they're centroid. We know from this movement in transformation space what the corresponding movement in the spatial domain should be, and we can just use that as constraints for a constraint deformation model. So in 2D, we use Takeo Igarashi's work. That's why you see this triangulation here. He gave us our code for that. For 3D, we use our Primo code. So basically now what we have is that the points that you see here moving in transformation space define constraints for a deformation model that drives the deformation of the shape. Okay, so let me walk through a whole example of the pipeline again. Here we start with our lizard, and we sample the object. So here you see two random samples that define a unique reflection plane, and we map that as a point in transformation space. And then we do this for another point pair, get another point, and we keep going and sort of slowly fill up the space. And you can see in this density plot here what's going on. You see accumulation. We get two clusters, and they correspond to the first symmetry around the head. So we can extract this part. This has a single reflective plane. And we also find the second cluster, which is this part at the back. And again, the fact that the clusters are not points reflects that the symmetries are not perfect. So there is some spread. Okay, so the first thing that we do is we try to make things symmetric locally. So we take one of these clusters, like the red one here, and here you see the extracted sample pair. So every point here now corresponds to a pair of points in this red shape. And now we compute a movement of these points in transformation space that actually symmetrizes the shape locally. Okay, so you can see the gray outline is the original shape, and the red one is now the symmetrized one, and the cluster has become significantly tighter. And we do the same for the blue part, and oops, this is what the object looks like. Looks very similar. But now you can see that these two clusters are actually more pronounced. And now to get this object into a global symmetry, we just merge these two clusters together. And again, this merging is very simple in transformation space. We just need to pull the points towards each other. But we know what kind of displacement that corresponds to in the spatial domain. And this is what happens if you apply that. You shrink the cluster, and eventually the object becomes perfectly symmetric. So what this slide here illustrates is what happens during this deformation. What you see in the bottom row is the point pair correspondences that you get at the end mapped back to the original. So this is what you don't know at the beginning. At the end, of course, you know which points are perfectly in correspondence. You don't know that at the beginning. But the algorithm iteratively detects symmetries, contracts, detects again, contracts. And by that, you can basically find this curve in transformation space, which reflects that curvy spine of the object. Okay, so let's look at some 3D examples. The world famous Stanford bunny. Here's the transformation plot. Now we're looking at rigid transforms, so rotation and translation and reflection. So a 6D space. We map that down to 2D to visualize it using multidimensional scaling, and this arc here is actually an artifact of that projection. But you can still see the two strong clusters. All the operations that we do are actually performed in a 6D space. So you see the two prominent symmetries, and if you run the optimization at the beginning, you will see a few subtle changes at the body and the ears. Basically here we're tightening the clusters, and then finally we merge the clusters, which rotates the head. So at the end you have a symmetric bunny, one tight cluster there. This lower cluster here actually corresponds to another symmetry that you get roughly around here. But you see, of course, that this is not perfect, especially if you look at the feet. Basically what's happening is that the symmetrization pulls this deformation model towards a symmetric shape, but the energy of the deformation model pulls against it. So it wants to keep the deformation as small as possible. The symmetry plane here goes roughly through this. So the energy is not, or the symmetrizing force is not strong enough to pull these feet into perfect symmetry, because they're too far off the original symmetry plane. Here's a more complicated example, again, the dragon. If you look closely, the head is quite asymmetric. So the horns, also the tongue, the chin, there's a lot of subtle variations in symmetry. Here's the projected transformation plot, and in particular this global asymmetry along the spine is something that we wanted to get. So again, I'll start the video. It starts with the head, so you see how things deform in the head region, then the feet get rotated and actually matched also together. The next part happens in the back feet and the tail, and then finally you see how the two big remaining clusters get merged and the object deforms. And then there's a final contraction stage at the end. And again, here you see the model. It's not perfect. Actually, in this view, you can't see it properly. But for example, back here, these features were too small to get captured by the detection. Also, if you look at the individual scales, we're not operating on this model. We only use about, I think, 2,000 random samples on this object. So it cannot capture the fine scale geometry. You would have to have a much higher sampling for that. Once you've symmetrized the object, just as a side remark, you can of course also do symmetric meshing, which can be important in certain finite element simulations, for example. Here's another example that I like. This is, maybe let me stop this video, which I can't. That's very difficult to control. Okay, let me explain to you what's happening here. Here we use the same idea to compute a correspondence between these two poses of a shape. And what's different now from before is that now we compute point pairs from one shape to the other only. But the rest is the same. So what happens is the symmetry detection will first find parts that can be rigidly mapped from this shape to the other. And these will be colored in blue. And then it symmetrizes the shape. That means it deforms one to match the other, or basically both to become to the center pose. And it does this iteratively. We still keep the poses apart for visualization, but you will see as the video evolves, always the biggest part that still remains gets matched and then gets symmetrized. So it starts with now it's at the head, and then it comes the shoulder. And you see the symmetrizing deformation in action here. Of course, these are not necessarily reasonable deformations in terms of the semantics of the human body, but we're just looking for a correspondence between these two shapes. And the nice thing is that this is fully automatic. It does not require any feature correspondences or markers computed up front. And if you then overlay the object, you see that we're almost perfect in terms of the correspondence. There's one thing again at the foot where the sampling was too different and the geometry was too different. We could not match this part of the toes to that part. But other than that, the algorithm caught the whole symmetry between the two shapes. Okay, so let me come to my conclusion. The central idea really was, let me recapitulate that before, to couple the spatial domain with the transformation space. In this transformation space, symmetry can be expressed much more naturally. You can just say that a cluster corresponds to symmetry. You can contract the cluster to enhance symmetries. These are very easy operations in transformation space. And through this closed form solution that I showed you, we can map them back to constraints in the spatial domain that then drive a deformation model. And I think the symmetry detection and enhancement is really just the beginning. There's lots of operations that one could think of. Symmetry-aware geometry processing in general, that you have geometry processing operations that detect and respect the symmetries. For example, if you do smoothing for noise removal, you do not destroy symmetries which can be important semantic features. You can do this in a sort of hierarchical fashion. One thing that we're working on right now is try to sort of reverse engineer things like these rules of growth or construction of biological artifacts, or let's say architectural models, and symmetry there also plays an important role. As I mentioned in the beginning, human perception is very susceptible to symmetries. Art and design are areas where symmetries play an important role. One thing that we also wanted to do is look at derived spaces. For example, you could look at motion data and analyze symmetries in there, or higher dimensional spaces. What I presented right up to now was not limited to any dimension. So you can do it in 2D, 3D, or ND. And there might be spaces where it's very difficult for us as humans to even detect symmetries. If you're looking at, say, a 6-dimensional phase space, for example, but this algorithm could automatically find it. And then the question would be, what does enhancing the symmetry in such a space mean? But this is something for future work. Okay, there's a couple of people that helped on this project that I want to thank, and of course also our funding agencies. And finish off here with just a list of the 2 papers that describe this work in more detail. And thanks for your attention. So, questions?
I was wondering if you have the thing symmetrized, and I don't know, you did some of this where you subtract the 2 things, and so you get differences, some sort of data compression technique from that. Mm-hmm. Is that what you intend?
So, I mean, what I showed in this castle example is basically you find a symmetry. In this case, because it was constructed the way the symmetries were perfect, you can just take out 1/2 and store that transformation. Right. And then from that, you can just reconstruct the original.
But if it's not perfect,
if it's not perfect,
can you somehow rather get get the symmetric part and the asymmetric part separated?
Right. Yeah. This one picture I showed, actually, it's this one here. This encodes the difference between perfect symmetry and the real model.
Okay.
So it basically says you take this part of the head, you reflect it, and then you need to add these kind of displacements to recover the original geometry. So you could think of this as, I mean, if the displacements are small, you have a good chance of encoding them very efficiently. So you could think of it as some kind of wavelet type transform and do the encoding. For example, these are just normal displacements. So the color coding is just the normal displacement that you need to recover the original. And we haven't really put this into some kind of working compression algorithm, but I think the potential is there. And you know, most acquired shapes will not have these perfect symmetries that you get from CAD models. So there you would have to deal with this issue.
What about trying to exaggerate the asymmetries? Have you thought about doing that?
We have done that, yes. There's one picture. Let me see if I can find the paper. Oh, yeah.
For faces, I think it would be interesting to do like a caricature.
Well, let me tell you. We thought of that. Oh, now I have these dual displays. So there is this picture down here where we did, oops, exactly this. Oh, this is really hard. Let me just turn this off. Oh, wait, maybe it won't. So what you see here is that the original is in the center, is symmetrized on the left, and then, actually if I scroll down also, the asymmetrized is on the right. And where's my mouse? And below you see the transform plots. Now, this is again operating on some sampling of the model. I think here we used 1,000 points. So it doesn't pick up small scale features like differences in the eyebrows or this little dimple here. But basically what we did is we symmetrized and then we just went the other way to get this one. And you can see that the asymmetries, like for example this little crease here, this dent in the cheek, the slight curviness of the nose get enhanced. People didn't like that picture so much. We thought it was kind of cute just to explore, but they said if you want to do exaggerations, there's better techniques, which I agree. But still, I think if you want to analyze, say, for example, biological specimen, because asymmetries are a key to recognize objects sometimes. Something that's very symmetric is very difficult for us to recognize or remember. It looks beautiful, but it doesn't look very unique. So this could be potentially be used to enhance this effect to maybe support some recognition algorithms. I don't know.
The algorithm, there was the cluster contraction step, and there was also a cluster merging.
Yeah.
And were those two implemented differently? And because
yeah, I mean conceptually, it's more an implementation issue. The reason we need this merging is that if you have, for example, a spine of this lizard, you have these two clusters, but they are merged by this curve. And you can actually just contract them, and if you have enough samples, they will automatically pull towards each other. But if you don't have enough samples, then this force is not strong enough. So basically what we do there is we take the cluster centers and move them in one step to their centroid. So this makes it just more robust. But conceptually, you could even think of contracting one cluster. If you start contracting it, it will start pulling in these other shapes. This is what you saw. Let's see if I can find it. So this is here we start the merging. So you see how the two clusters get pulled towards each other, and here they're already one. And now what's happening is we just contract this, and it will suck in the rest of the tail because it's already very close. And when you do some more contraction, it's very difficult to see in this transform image. But at this stage, it's just contraction. And in theory, if you look at this plot here, what we have is we have two strong clusters. One is here and one is here, I think. So that corresponds to this part and that part. And we could just, say a cluster is this, we contract it, it will move the rest slowly in. But if you have too few points here, this connection will break at some point. So you will not be able to bend around the whole model because the force of the deformation will pull against it. So the deformation model actually provides the regularization, if you will. Symmetrization tries to make it symmetric, and the deformation tries to move it as little as possible. So if you don't have enough points here, then that force will not be strong enough. So that's why we say, okay, let's just take all these points and move them here and use that as constraints.
The merge step is the one that involves the primo deformation of the space?
Both use it. I mean, for example, if you look at, let's say, look at the bunny video. At the beginning, we do this cluster contraction. You would probably not need it. You see that things are happening here now to the ears. They get slightly deformed.
The least squares functional that solves for the optimal plane and the minimal
yeah.
deformation.
The thing is that we're not operating on the entire full resolution model. So we just have a bunch of displacement constraints for some points on the ears, for example. And they then get used as constraints of the primo model, but the intermediate vertices just get dragged along. Because we want to avoid having to have like 60,000 points on this bunny, because the deformation has much fewer degrees of freedom. So that's basically the idea. But conceptually, you could also, if you wanted to operate on the full resolution, and then you probably wouldn't need primo for the contraction. In the 2D example, we didn't use that. We only used it for the merging.
Once it's been symmetrized, you can have a symmetric remesh,
Mm-hmm.
and then can you bring it back into the original pose, create a deformation?
Yeah, we can do that. We're actually thinking of this as an application, for example, if you want to do finite element simulation. So it's very easy to do. Where's the symmetric remesh? It's very easy to do some kind of meshing like this. And of course, it's trivial to invert the deformation. And we know the path of the vertices, we can just go back. I'm not entirely sure for which application this would be useful. We were thinking of, a lot of finite element simulations might want to have the symmetric meshing, but it's not clear to me actually. Because for example, if you have, say, a fluid flow through a bent pipe, the flow will not be symmetric. It's questionable if a symmetric meshing will help or make it better, but I'm sure there might be some applications where this might be useful. But it is fully invertible.
Thank you very much.
All right, thanks.